Start new stuff. Do you guys have questions on 3-1 things? Or I guess prior even would be okay. Mackenzie? From section 3-1, number 65? Okay. Grab that. All right. It says find a cubic function ax cubed plus bx squared plus cx plus d whose graph has horizontal tangents at the points -2, 6 and 2, 0. So when it says horizontal tangent, that means that the slope at these points should be 0. So to do that, I'm going to look at the derivative. So if I have my general cubic function that they've given me, I'm going to first find the derivative. Okay with that? And then we can say that the derivative is equal to 0 at these points. So that's going to form us a system of two equations. When I simplify this down, what do I get? I have 12a minus 4b plus c is equal to 0. And here we have 12a plus 4b plus c is equal to 0. So if I solve this system, if I just subtract the first equation from the second equation, I would get that 8b is equal to 0, or that b is 0. All right, so I have that. And then let's see, what else can I do with there? I'm going to have a problem trying to solve for a and c, right? Well, I can say that 24a plus 2c is equal to 0. I don't know if this is going to be helpful or not. So c is going to equal negative 12a. I don't know if that'll work out for me to be helpful or not. Okay. I can also, if I go back to the original equation, I can use these 2 points to create another system. So I can say that 6 is equal to a, not x, but negative 2 cubed plus 0, negative 2 squared. And then I'm going to go ahead and make my substitution with the c. I'll just write that as minus 12a times negative 2 plus d. And then my other is going to be 0 equals a times positive 2 cubed plus 0 times positive 2 squared minus 12a times 2 plus d. That'll form another system for me. Is that still doing okay? I'm using that substitution for C that I found from the derivative. Felt like that's going to at least get me down to now a two-variable system that I can deal with. That's probably the sneakiest observation, is that you could still do something with that. So I have negative 8a plus 24a plus d is equal to 6. And then I have positive 8a minus 24a plus d is equal to 6. Nope. Is equal to 0. Sorry. And I combine my like terms, so I'm going to have 16a plus d is equal to 6. And then I'll have negative 16a plus d is equal to 0. So I get 2d is equal to 6, or d is equal to 3. And then if I plug that back through, I'd have 16a plus d is equal to plus 3 is equal to 6. So a should be 3 over 16. And then I can say that c is negative 12 times a, 3 over 16, which reduces down to negative 9/4. So those would be my values for a, b, c, and d for my general cubic. So y equals 3 over 16 x cubed plus 0x squared minus 9 over 4x plus 3. Is that okay, Mackenzie? So the algebra was rough there. The calculus part should have been relatively easy, right? We're just making the observation that if we're talking about a horizontal tangent, that's where the derivative is going to be equal to 0. So we just take our general function, differentiate it, and then plug in those values of x set equal to 0, and we start solving our system. The fact we had to go back and forth between the function and the derivative was kind of sneaky to figure out the a, b's, and c's. It's got it all on one screen for you. Follow-up question on this.
So you just go over it where 6 equals a minus 2, like where did you get 6 equals?
I took the point negative 2, 6 is a point on my original function. So I plugged that 6 in for the y, right, and then the negative 2 in for the x's into the original, the y equals version rather than the dy dx version.
The y equals the slope.
Well, the y in this case is the point. It's right, the y coordinate of the point. Right. In the derivative, the y coordinate from the point means nothing to me. Okay. But the x, we're told there's a horizontal tangent there, so it tells me that the derivative is equal to 0.
Okay. Gotcha. Where is the horizontal?
Exactly. Yep. Mia. 23. Okay. Oh, where did that go? I didn't want it there. Okay. So again, we're just looking to take the derivative. So the first thing I'm going to do right now, this is written as a quotient, right? I need to rewrite this so it's just like a polynomial. So I'm just going to rewrite this, instead of having one big common denominator, I'm going to write it so each term has its own separate common denominator. I wrote a 3 down there. Cool with that, Mia? Okay. And then I remember that a square root is the same as an x to the 1/2. And I notice these first two terms then can reduce. And the last term I can just write as with a negative exponent, since it's in the denominator. And now I'm at a good spot to where differentiating is going to be easy, right? So when I take the derivative, I'm going to have 3 over 2, x to the 1/2, 4 times 1/2 times x to the negative 1/2, plus 3 times negative 1/2 x to the negative 3/2. And now it's just a matter of like cleaning things up. And that's okay, or you could rewrite this with like common denominators and like radicals back in there and all that nonsense, but I think that that's fine. The rest of it's just going to be algebra. You know what I mean? We did the calculus part. Does that look okay, Mia? Yep. And again, the trick was getting it to here that made it easy to differentiate. So again, the calculus part, pretty easy. The algebra part before it, to get it to a point where the calculus was easy, a little sneaky. Mackenzie. 57, you say? Okay. Let's see. Spot over there. Okay. All right, it says find the equation of the normal line to the parabola yada 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 that is going to be parallel to the line yada yada yada. Okay, so what I'm going to need to do is, first things first, I need to take this line and figure out its slope, right? So to do that, I'm just going to rewrite it so it's in slope-intercept form. So I can see that that line has slope of 1/3. Everybody's cool with that? So that tells me the slope for my normal line also needs to be 1/3. Cool with that. What I'm going to need, though, is a point for that normal line. Okay. The slope for my normal line also has to be 1/3 because it says that it wants the normal to be parallel to that line. What we still need to find, though, is the point that that normal line needs to go through. So this tells me if the slope for the normal line has to be 1/3, the slope for the tangent line has to be -3, right? They're negative reciprocals. That's what I'm going to need there, because that's going to be the same thing as, or it's going to allow me to find where the derivative is equal to -3. So I'm going to be solving the derivative, looking for a place where the x, a location, I'm looking for an x that is equal to -3. Everybody's okay there? So that point on my normal line needs to have the x-coordinate 1. What is its y-coordinate going to be? I'm going to have to go back to the function now and plug that x value in. So when I do that, I get the y-coordinate is 0. So now that I have the point and the slope, I can write my normal line. So that looks like it. Paul?
So what is that? I can't really read out. It says f plus something equals -3.
M tan, the slope of the tangent line. So let's just graph all this stuff and make sure that the picture supports what we're found here, right? We have these fancy graphing calculators. We might as well use that. So here's my parabola. And then this one that I'll do as a dashed line is going to be the line that we're looking to be parallel to. And then this one will be my normal line. And I'll do that with a thick line. We'll graph that just on the standard window. So there's my parabola. There's the line. There's my normal that's tangent, or that is parallel to that other line. So that all looks good to me. Victoria?
So the reason they give us like the second division is just to find the slope.
Correct. Is I needed that to get the slope for my normal line, and I needed the slope for my normal line to figure out the point that I needed from on the original function.
So then like for 55, since it's tangent, we would just find the slope in the second equation and like
Right. So yeah, so you just would skip this step basically. You just take the slope from the line and plug it in for the derivative directly. So on this problem, because we're dealing with a normal line instead of a tangent line, we had to figure out the slope that we needed to plug into the derivative. We had to do this piece where we flipped it. You can skip that if you're just looking for something that's a tangent line that's parallel to another line.
for a tangent line, we don't use the tangent slope,
We have it,
which is like
right? So instead of finding the normal slope here, you're finding the slope for the tangent line because it's parallel lines have the same slopes. So in 55, where it says you have a tangent line that's parallel to this, you just found the slope of the tangent line immediately.
we find the slope of the line.
Right, it's basically given to you. So that's what you'd be plugging in here. You don't have to deal with any reciprocals or anything. But it's ostensibly the same process. Mackenzie?
Why did you put the one next to the other equations?
So I'm looking to write the equation for the normal line. I need the slope, and I need a point from my function. So what I did is I found the location where the x is going to give me the correct slope, but to figure out the y-coordinate that paired with it, I had to plug it back into the original function, not the derivative. If I plugged it back into the derivative, what would I get back? -3, right? Because that's what I solved for. You know what I mean? Hopefully, if you would have done that on accident, it would have been pretty clear immediately, like, wait a minute, that's just what I solved for. Of course I'm going to get -3 back. That's not what I want. Again, with these kinds of problems, the hardest part about it is keeping straight, like, where should I be plugging this in, the function or the derivative? And what should I be solving, the function or the derivative? It's going to be the going back and forth between them that kind of gets confusing. Okay with that? Okay. Anybody else with questions from this section? You guys asked about some good ones, though. Are we happy with the answers that Mr. Kulik gave? This was pretty clear as to like how to do stuff and why I'm doing things. Okay. I'm trying very hard to make sure I'm giving you guys good explanations and like really thoroughly talking through things. If you are still confused, though, or if you're not sure, or you have a hypothetical, like feel free to ask for some clarification or whatever. You know, this time is important time for all of us to make sure that we're, you know, getting some feedback on the things that we've done already. Okay. All right. So today, we're going to talk about the product and quotient rules. So we'll start with the product. And what the product rule is going to describe for us is it's going to ask, how do we do something like this, where we're going to take the derivative of the product of two functions. Now, naively, maybe we'd think that maybe the derivative works the same way as the limit does, right? If I took the limit of the product, I could just have the product of the limits. So maybe I think I can just do that, right? That would be ideal. That seems like the natural thing to do. Well, let's try something that we can do it two ways. So let's say we have the function x squared, y equals x squared. I know that if I take the derivative of this, I get 2x. If I think about y equals x squared as x times x, that's still the same thing, right? And I do what I did above, I'd get and what do I notice? That's not how we take a product. Okay, well, what should I do if my guess to the formula didn't really test out? Go back to the definition. Okay? So let's try that. So I'm going to define a function capital F. Hi. Sienna, for you. Good luck. You're welcome. That I'm going to define as just some function f of x times some other function g of x. The derivative of this then would be the limit as x approaches h of f of x plus h times g of x plus h minus f of x times g of x all over h. And if I take a look at this, well, I don't know, Mr. Gulick, doesn't look like there's anything that I can separate or like any algebra stuff I can rearrange with this, right? So obviously what I'm going to have to do, it's going to be some sneaky jerk kind of move here. It is. Here's what Mr. Gulick's going to do. He's going to add an f of x plus h times g of x, and then also right after subtract an f of x plus h times g of x. Is it okay to do that? Definitely, right? It's just like doing nothing at all. And actually, now that I look at my notes, I think I did this in the other order. I subtracted it, then added it. It doesn't really matter, other than that avoids me having to do a rearranging later. Everybody's cool with that? What I did is still legal? You ask, Mr. Kulik, why would you want to do that? Well, if I form two groups now, I see that I have some factor by grouping possibilities where the piece that's going to be left over inside the group is going to look a lot like a derivative definition. Everybody cool? Okay. So now what I'm going to do is I'm going to break this fraction into two fractions with a common denominator. And I'm going to write that common denominator only under the factored piece. And it's okay to do that because we're just talking about multiplication, right? What does that look like? It's the derivative of g, right? What's this look like? The derivative of f, right? So what I'm going to do is I'm just going to go ahead and use my limit laws to kind of distribute that limit throughout the piece. So I have a limit of f of x plus h. I have a limit attached to this difference quotient. I have a limit attached to the g of x. And I have a limit attached to the last difference quotient. Okay, so what is the limit as h approaches 0 of f of x plus h? F of x. Just doing a direct substitution. The limit as h approaches 0 of g of x plus h minus g of x all over h is the definition of the derivative of g. The limit as h approaches 0 of g of x is just g of x. And the limit as h approaches 0 of f of x plus h minus f of x all over h is just the definition for the derivative of f. So this is our product rule. Let's do some examples. So let's say we have f of x equals x times e to the x. And let's say we want to take the first derivative here. One thing I should notice is that I have two distinct functions that are being multiplied together. Everybody see that? Notice that there is no way to combine the like terms of these two functions. At least not a kind of silly, not a non-silly way to do it. I mean, you could write x as e to the ln x or something, but that didn't really helping us much for the tools that we have. So if we use the product property, I'm going to think about this is my f of x, and this is my g of x. So I'm going to have x times the derivative of e to the x plus e to the x times the derivative of f. And as you get better at this, we're going to stop writing out like all the work for these unless it's like absurdly complicated. But for the first times, while we're just getting used to using the product rule, I'm going to continue to just kind of write them out. So that gives me x, and the derivative of e to the x is e to the x, good, plus, and then I'm going to have an e to the x, and the derivative of x is 1. So this just becomes, you could write it as x e to the x plus e to the x, or you could write it as like 1 plus x times e to the x. Maybe I'll write it as x plus 1. It's a little easier to see it there. But either is okay. What if I wanted the second derivative of that? I wrote two versions of my answer here. Which one would be the better one to use if I'm going to take the derivative of it again? The yellow one. Because it's already written as a sum of two things rather than a product of two things. Now, I could use the green one, but what would I have to do on the green one? Well, I'd have to do a product property. On the yellow one, I still have to do a product property, but it feels like it's going to be a potentially easier product property to do. But it doesn't really matter here. So x times the derivative of e to the x plus e to the x times the derivative of x, and then I plus the derivative of e to the x. This stuff is coming from the derivative of that, and this part is coming from the derivative of that. Do we need to do a one intermediate step?
No, so
So when I take the derivative of x times e to the x, that's a product property. But the derivative of e to the x is just, just a normal derivative.
So the green part that you highlighted, since there's like three variables, or like I don't know what it's called, but that makes sense. Like there's an extra e to the x, so that there's three, but on the product rule is only f of x and g of x.
But it's not being multiplied.
Right, so then what do we do with that one? It's just normal.
So my derivative distributes, right? So I have the derivative of e to the x plus the derivative, right? And the piece in yellow needs a product property. The piece in green, though, doesn't. It's just like a regular, right, there's no multiplication, just a regular derivative. So I have x times e to the x plus e to the x times 1 plus e to the x. So that's going to give me x e to the x plus 2 e to the x's. Or you could write it as x plus 2 e to the x. Quick in your head, the 100th derivative. Yep. Mackenzie. So I start by distributing the derivative. So that's giving me the derivative of the first piece plus the derivative of the second piece. The piece in yellow is a product, so I had to use the product property or the product rule. And the piece in green, well, a regular derivative, so I didn't have to do any property there, just left it. Is that?
So there might be like, say there's like 4 sections. If two things are multiplying by each other, you would use the product property on this.
Yes.
Like 4 times or 5 times.
If you had like 3 things multiplied together, I think I have an example of that coming up. It means that you're going to have to do like 2 levels of the product property. You'll have to do like a product property inside of another product property.
Okay.
Should we do an example like that? I don't know that I have 3 different kinds of functions. That's just like another hypothetical example. I just asked what would the derivative of the 100th derivative be? Just looking at the pattern. The first derivative we had x plus 1 e to the x. The second derivative we had x plus 2 e to the x. The idea was that each time we do it, you're just going to add up with 1 more e to the x. So let's say we have a plus b t times the square root of t, and we're looking to take the derivative of this, obviously with respect to t, since that's the independent variable quoted in the function. How do you want to do this? Well, there's 2 routes you could take, right? You could take the derivative as it's currently written, but what are you going to have to do that? That would require a product property because you have things that are multiplied together. prefer not. What we can do instead is we could think about this as that, and there's no product property needed. So just because you have this new hammer, shouldn't look at every problem as a nail, right? Use your algebra, make the derivatives easier. If you can avoid having to do a product property by distributing or foiling or whatever, do that.
How did you get 18?
How did I get?
Oh, because you just write those into.
Derivative.
Okay.
We're okay?
Yep.
Okay. Let's do, yeah, Taylor.
Why is the a? Why is it a over 2 to the negative 1/2 and then is 3b over 2?
So when I did the power property, I multiplied a by 1/2, a over 2, and I multiplied b by 3 over 2.
Why is b? Oh, because it has a t already in the initial. Why is it 3 over 2? It already has it.
Because that's how you, the power property, the derivative of x to the n is n times x to the n minus 1.
Yeah.
So it had a 3 over 2 in the exponent, so I multiply that to the coefficient, and then I subtracted 1 in the exponent. Is that, you're cool?
Yeah.
Okay.
It was just I didn't see the t on the b in the
Oh.
very beginning, so I didn't know why it was different than the a.
Gotcha.
But I get it now.
Okay. All right. Let's say we have that f of x is equal to the square root of x times g of x. And we know g of 4 is 2, g prime of 4 is 3, and we want to find f prime of 4. So the first thing I would do is I'm going to take the derivative of f in general. Notice that the f is the product of two functions. So I will be using the product property here. Keep saying property. I really mean product rule. And I guess as long as I'm going to do that, I might as well write it as 1/2 in there. Everybody's cool with what I did there for my initial setup? Let's take some derivatives now. So the derivative of g to the x, I'm just going to write as g prime. The derivative of x to 1/2 is going to be 1/2 x to the negative 1/2. Everybody's feels good so far? Now let's do f prime of 4. All that means is I'm going to be plugging 4s in for x Everybody's cool there? Now the square root of 4 is 2. I'm told that the g prime of 4, I'm told in the problem was 3. I'm told g of 4 is 2. And now I just have to do 1/2 4 to the negative 1/2. What's 4 to the 1/2? 2. Okay, so what's 4 to the negative 1/2? 1/2. And then 1/2 times 1/2 is 1/4. So that's what I'm going to put there. You could type that into your calculator, though, too, if you needed to. So I have 6 plus 1/2, or 6.5. Is everybody okay with what I did there? So Victoria had kind of asked about this situation where maybe we had more than 2 things multiplied together. We don't have 2 different kinds of functions that we can't algebraically combine together right now to deal with, so I'm just going to do this kind of in general to just show you what I mean, where we're going to have product rules inside of product rules. Everybody's okay? So what I'm going to do is I'm going to treat, this will be my first product rule, where I'm going to think of the f of x times g of x as one thing. So I'd have h of x times the derivative of f of x times g of x plus f of x times g of x times the derivative of h of x and I notice here to do that derivative is another product property. So that's going to be g of x times the derivative of f of x plus f of x times the derivative of g of x, and then all that stuff that I had written before. So that's what I mean, where I have a product rule inside of another product rule. And if you had 4 things or 5 things or 6 things, you could still kind of do the same. You're just going to have like lots of product rules inside of product rules inside of product rules. But it's still fine. Mackenzie? Because we're not taking the derivative of that stuff, right? There's no d dx in front of it. Is that okay? Okay. All right. So the quotient property. So this is going to be if we have two functions dividing each other. Actually, it's probably, I'll write the notation this way to be more clear. So this is our quotient property. So this product property and quotient property definitely 100% need to have these memorized. Okay. You'll use them all the time. The AP exam is expecting them to be memorized. If you need to make some flashcards, make some flashcards or a Quizlet or whatever you guys do to practice your study your memorization stuff. But these derivative rules that we're kind of creating in this chapter, 100% things that we have to have memorized. Sophia?
When do you use like the apostrophe versus the D over DX?
They're interchangeable, so they mean the same thing. It just kind of, I think that when you have an equation, like an actual problem given, like this, blah, 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 x, da, 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 times, da, 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 the ddx makes that easy notation to use to put that in front of whatever you're taking the derivative of. But in general, if we just have some function f of x, I'd probably just write f prime because it's way less symbols to call the derivative rather than ddx of f of x. I did it up there before because I was trying to use the same notation that we were using inside of a problem. But they mean the same thing. They could be used interchangeably. All right. I'm going to skip the proof on this today because it's just kind of messy. It's like it's almost a full page for me. I don't know if it's going to add a whole lot. We did the product property. It's the similar idea. It's just a little messier. Let's just go to some examples because this is, again, the piece that we're going to be the more practical piece. Okay, so clearly a quotient, right? So using the product property, I have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Again, as you get more comfortable with these rules, you don't need to write this first intermediate step where all I'm doing is just kind of like taking the stuff that I have and dumping it into the formula for the product or quotient rules. But these are notes, and I think it's enormously helpful if you go back and you look at your notes that you can see what the step was that we're doing. All right, so let's evaluate some of these derivatives. The derivative of x squared plus x minus 2 is going to be 2x plus 1. The derivative of x cubed plus 6 is going to be 3x. And from here, we're just going to FOIL out that piece, distribute out that piece. Should I bother to FOIL out the denominator? I would not yet. Well, because if there's any reducing that I could possibly do in the future, I would need the denominator in factored form, which it's already in. So until I get to the very end, I'm not touching that denominator. And I would only touch it if the multiple choice question that I was doing had the denominator all multiplied out. Right. If it was just doing this for Mr. Kulik, I would never touch that denominator unless it felt like I was going to be able to make the problem simpler by doing so. So like if it was like something under a square root with the squared around it, sure, I would reduce that. But in general, I probably am not touching the denominator. Okay, so we got 2x the fourth plus x cubed plus 12x plus 6 minus 3x cubed minus 3x squared plus 6x. And then if I combine my like terms, the only x to the fourths I have are here. And then I have 1x cubed minus 3x cubed is going to give me minus 2x cubed. And then that's my only squared term. So I have minus 3x squared. And then I have a 12x and a 6x. That'll give me an 18x plus 6. And yes.
For the 3x it's multiplying, isn't it like 3x to the power of 2?
Oh, goodness gracious. I did mess that up, huh? Yep. So that should be squared. That should be to the fourth then. That'll be cubed. That'll be squared. Oh boy, Mr. Kulik. Now you did it. Victoria, good catch, but try to do it earlier so I don't have to go back and edit so much stuff. I'm just teasing, as if it's your fault that I made a mistake. I should be more annoyed that everybody else let me go that far. Way to go, guys. Or that I didn't look at my own notes to realize that I had made a mistake. Now, I would give that polynomial on top a cursory glance to see if there's any obvious factoring thing I can do to that. But with 5 terms, it's not very likely that there's anything good to do with it. There's no greatest common factor, and past that, I'm not really messing with it. I would say that almost assuredly that's going to be the best we can do. Which I'm happy with, right? And notice that I didn't even bother with the denominator multiplying out. I would say that you don't need to do that unless there's some obvious reason why it would make the problem simpler. But me foiling that thing out is not going to allow me to reduce anything. And if it's not going to get me any reducing, then I don't want any part of it. All right, let's say I want to write the tangent line to this function f of x at the point 1 comma e over 2. If I want the tangent line, what do I need? Yeah, I need the slope here at this point, x equals 1, and then I need the point that I'm given. Everybody agree with that? So the only thing I really need to get is that slope. To get the slope, I need the derivative. So let's do that. Okay. Quotient rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared derivative of e to the x is just e to the x. The derivative of 1 plus x squared is just 2x. And now, could I clean this up? Sure, but what do I really want here? I just want the numeric value when f is, when the derivative is equal, or when the derivative, I want the numeric value of the derivative at 1. So why would I bother cleaning all that stuff up if all I'm going to do is plug 1 into it anyways and get a number out of it, right? Save yourself the hassle. Just plug the 1 in. You guys good with that? So when I do that, I just get 2e minus 2e over 4, which is 0. Hey! The slope for my tangent line is just 0. It's cool, like that's the easiest tangent line to write. How do I write the equation for my tangent line if the slope is 0? It's just going to be the horizontal line that goes through the y-coordinate of that point. That's it. Whoa! That's dope, Mr. Kulik.
No, but like I'm not like like the ACG.
So again, this is a problem that has like a clear geometric meaning to it, right? Like we should be able to look at the picture and be able to tell if we've done this correctly. So I'm going to type in my derivative. I'm going to type in my tangent line. And I might even, just to make this fancy, I'm going to type in the point that we're given, which is 1 comma e over 2. So there's my point 1 comma e over 2. There's my tangent to it. Maybe that would look better if I made that a dashed line instead of a solid. So here's my function. Here's my tangent. Looks right to me. If you really wanted to get careful, you could zoom in there and just look from 0 to 2 or whatever. But not surprisingly, it looks pretty, the function's pretty darn flat there, which matches what we got. You guys happy? So, again, another section, that's another section down. Theoretically, was there anything like really complicated idea-wise in here? Not really, right? You got introduced to a new derivative rule, or new pair of derivative rules that you get to play with now that'll make the stuff that we can take derivatives of without having to go back to the definition that much wider. Oops, 959. Yes. Yes.